Hey everyone, we are going to head into chapter 1. Hopefully, everyone has gone through the review that I posted. It also is the beginning portion of chapter 1. And we are going to now head into more of the new material with some material that you should see as a reminder from general chemistry. And again, how it fits into what we'll be looking at in organic chemistry. So, the outline for this section of chapter 1, we're going to be talking about how to draw structures. This is something that we'll be using a lot in organic chemistry, and I want you to really work on your drawing abilities and practice drawing a lot. We'll be talking about how we use curved arrows in organic chemistry, a reminder on resonance structure and curved arrows, and molecular geometry. So you should have already seen some molecular geometry in the past, but here we're going to talk about how molecular geometry and shape can affect things like polarity and dipole moment. So into drawing structures. One of the key things we're going to be doing is drawing in organic chemistry. And we think about structures of a molecule at various levels. So one of the ways you should have already seen is a composition of a molecule that's captured by its molecular formula. That is just the listing of how many of each element is in that particular molecule. So in this case, we have a molecule that is C4H10O. This is just the molecular formula. Another way we can think about it is through constitution or connectivity of a molecule, which can be captured by something called the structural formula. And this shows how atoms are connected. So here now we've broken apart each of the elements into where they are in the structure. You can see there's a CH3 group next to a CH2 group, next to an oxygen, next to another CH2 group, next to another CH3 group. So again, this just shows the connectivity, but it is still in a formula. There's no actual drawing of bonds included here. And lastly, and probably the most common way that we'll be drawing is captured by structural drawing, which shows the position of the atoms in space. This actually will show kind of some angular positioning and how they are relative to each other. So it's not condensed, it's not just showing how they're connected, it's also showing where they are in space. So here you can see this is the structural drawing of the formula that we gave. Here is the CH3 group, here is the CH2 group, here's the oxygen in the middle, another CH2 group, and another CH3 group. But again, you can see how they are positioned in space using a structural drawing. Now, one thing that is going to occur a lot when going from formula to drawing is that there are isomers. So a reminder, compounds can have identical structures on a broad level, but they can differ on a specific level. And these compounds are called isomer, meaning constitutional isomers can have the same composition. That means the same molecular formula, same number of elements in the formula, but they're differ on how those atoms are connected to each other. So here's an example here, ethanol and dimethyl ether. If you actually write out their molecular formula, if we count everything, so you can see ethanol has 2 carbons, C2. It has 1, 2, 3, 4, 5, 6 hydrogens, H6, and it has an oxygen. And dimethyl ether, 1, 2 carbons, 1, 2, 3, 4, 5, 6 hydrogens, and an oxygen. So again, they have the same molecular formula, but as you can see in this presentation, they have different connectivity, and this makes them very different. They can have different physical properties and different chemical properties. So we're going to be talking a lot about different isomers and how one formula could be a different composition, different entire chemical based on structure. So let's do a practice of this. Let's practice going from formula and understanding how many isomers can exist. So here we have the formula C3H7Cl. Now I'm going to write this out so you can think about going from kind of the Lewis structure to drawing it in a connected way. So we know that, first of all, we have 3 carbons. I like to start with the carbons. When we're in organic chemistry, carbons are usually going to be the backbone of almost all the structures. And so it's wise to start with drawing these out. So there are 3 carbons. I'm going to think about them connected to each other. So one way we can connect them is in a line. This is always the way that I start connections. So 3 carbons in a line. I want you to think about it. Is there any other way that I can break a bond and connect a carbon in a different position? So if I connected this one at this end, it actually doesn't make a difference. It's still just 3 carbons in a straight line. Even if I break this one off and I try to connect it here, technically this is still just 1 line of carbons. So 3 carbons actually cannot be rearranged in any different way. They can only ever just be rearranged together in a line. That's something you can always, that's a piece of information you can always use. So let's draw our 3 carbons. Now, we know that there are 7 hydrogens, and I'm going to fill hydrogens in using the piece of information I talked to you about in review. I told you that carbons always like to make 4 bonds. So let's just start filling hydrogens in with that piece of information, knowing that carbons should be making 4 bonds. And we'll start at the end here. So this carbon at the end is already making 1 bond. That means it wants to make 3 other bonds. It's generally going to then be filled in by our hydrogens. So here's a hydrogen, here's a hydrogen, here's a hydrogen. Okay, let's look at our next carbon. This carbon is currently making 2 bonds. That means it has 2 positions open for bonding. Let's fill those with more hydrogens. Here's a hydrogen, and here's a hydrogen. So far I have 5 hydrogens of my 7 in the formula. So let's keep going. This last carbon is making 1 bond. That means that it's open to 3 bonds. Now I only have 2 hydrogens left. I've used 5 of them. So I'm going to put 2 of them here. Here's a hydrogen, and here's a hydrogen. That's 1 spot open left for this last carbon to make a bond. And we know that we have chlorine. If you look at chlorine's valence shell, I'll draw it here. It has 7 electrons, 1, 2, 3, 4, 5, 6, 7. Notice there is 1 electron unpaired. That means that chlorine tends to make 1 single bond. So it makes sense that this chlorine would fill the last position here on this carbon. Chlorine is making 1 bond, it's happy. All of the carbons are making 4 bonds, they're happy. And we have the correct number of everything in our molecular formula. So this is just to start. Now we know that we have drawn out at least 1 iteration of an isomer. So now let's think about ways that we could make this different. So something we will talk about and learn is that positions on a carbon, for example, these hydrogens and this chlorine, are equal. And we're going to talk more about this. That's because this carbon can rotate. So what I mean is, if I drew this like this, with the chlorine here in the middle, this is actually in the same position. This is rotated into position. So here on this carbon is not a structural change. It has not changed positions. It's still connected to the same carbon. So this is not a different molecule. Now, if we change the actual position of the chlorine, we will get an isomer. So let's try shifting the chlorine to the carbon in the middle. That structure would look like this. We have our three carbons. And now we've put a chlorine on the middle carbon. I'm going to put my hydrogens back. There's 3, 4, 5, 6, 7. Again, all of my carbons are making 4 bonds. And now we have our chlorine in the middle. This is a constitutional isomer. We have changed the positioning of the bonds. The chlorine is now connected to the second carbon instead of to the end carbon. Now, there's one other position open, and that is the carbon at the very beginning, the first carbon. If we were to draw this structure in which chlorine was bonded to the very first carbon, instead of the middle or the end. So I will draw that version. Here's that version. This, a lot of people would be confused into thinking is an isomer. You'd say, oh, well, I moved the position of the chlorine. And this is tricky because technically this molecule and this molecule are the same. They have symmetry. You can superimpose them on each other. If I were to flip this molecule across this axis right here, across this vertical axis, you'd see that it would be the first one that we drew. It would look exactly the same. That means that they are the same. If you can pick up the molecule mentally, of course, and you can rotate it and fit it back onto the molecule you've previously drawn, that actually means that they are the same molecule. We're going to practice this using some 3D online in lab, actually, so you can kind of visualize it better. But here you can see if you're able to draw a mirror, a vertical axis, and you can rotate the molecule over it, and they superimpose on each other, they are in fact the same molecule. So this is not a constitutional isomer. It is just the same molecule as the first molecule. That means for the question, how many constitutional isomers can we make? We've now moved the chlorine into all of the potential positions, meaning that there are only 2 different isomers for this particular compound. Okay, so that is a practice on isomers. Let's talk more about just generally going between this condensed and bond line formula. Remember, condensed formulas are textual and they usually list atoms in their connectivity. That's the one that I've shown here, in which you just have the formula listed out, showing the connectivity of the atoms, but you don't show where they are in space. So you can go from a line drawing to a condensed formula, as in the case here. This point in our line drawing is a carbon, and so we know that this is a CH3 group. It is connected to an oxygen, so the next would be oxygen in our list. The next to right would be another carbon, and notice this one has 2 hydrogens on it, so it would be a CH2 group. Connected lastly to a carbon with 3 hydrogens, a 3 group. And that's how this formula was generated here. Another way we can draw things out is using the bond line formula. In this case, it omits the labels for carbon atoms and omits hydrogens. This is the most common way organic chemists will draw chemicals, by both omitting the actual carbon atom. So just like in the instance above, notice that each point that I drew was a carbon atom, and I didn't actually write the symbol carbon. So carbon atoms instead are every point in the molecule, and we omit hydrogens in the drawing. So hydrogens are implied. This is why I said it's important to always know how many bonds carbon makes, because any bonds that are not shown in a molecule, you have to assume are being made with hydrogens. So we have to, again, assume that the octet rule is satisfied, assume that each carbon is making 4 total bonds. So here's an example here. It's the same molecule from above. Again, I'm going to point out that every point along the molecule, here, here, and here, we're assuming that implies a carbon. Every point is a carbon. And we are not going to draw the hydrogens. So that's how we get this. Here's our carbon, the first carbon connected to an oxygen, and then the second carbon and the third carbon. This would be the structure you ultimately would draw. And we know that it's equal to this structure. We know that all of those hydrogens are there, and we also know that each of those points is a carbon. Okay, so let's do another practice, expanding these bond line formulas. In this case, we're going to go from the bond line formula, and I am going to ask that we draw it ultimately showing all of the carbons, hydrogens, and lone pairs that you would in a Lewis structure. So you can kind of understand how you go between the two. So the first thing you want to do if you're given a bond line formula and you want to draw it in the full Lewis structure is you want to draw the carbon atoms. So figure out where each point is and make that a carbon atom. So here on our structure, I'm going to show the points. This is a point, 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 point. Notice that this point up at the top is connected to an oxygen atom. So if you see any other element instead of just a regular point, you leave that element. It's not a carbon, then an oxygen. This is just an oxygen. Now this one might be a little bit confusing, but even points at the end are carbons as well. So don't forget about those ones. So here, this would look like this. We have a carbon, line, another carbon, line, carbon. So I'm just drawing out that 5-membered ring with carbons. And then up top here, we have our OH group. That stays the same. And 2 lines and another carbon. So I'm just copying everything but making the points carbons. Okay, so once we have that, the next thing you want to do is draw out all of the hydrogens that we're missing. This is to satisfy the octet rule. Don't be scared by these complex molecules right now. Just remember again what I said, which is that every carbon ultimately wants to make 4 bonds. So in this case, we have our molecule here. I'm going to start with the top carbon at the point. Notice it is making 3 bonds, 1, 2, 3. So the last bond will have a hydrogen. This next carbon has 2 bonds. So it has 2 hydrogens. This carbon also has 2 bonds going to it. So it has 2 hydrogens. Same for this one. And this carbon here, let's not forget about this. Let's count how many bonds it has. It has 1 going to the tip, 2 going down. And this double bond, remember, counts as 2 bonds. So that's 3, 4. This carbon doesn't need any hydrogens because it has 4 bonds already. What about the carbon on the very end? It has a double bond, which counts as 2. So 1, 2, 3, 4. All right. That is how you draw in your implicit hydrogens. So once we have drawn our hydrogens, and looks like I made a mistake on mine, this hydrogen shouldn't be here. You're then going to add lone pairs on heteroatoms and or on carbons if they need them. Now, in this case, all of our carbons have been satisfied with our hydrogens, but there is one atom we haven't talked about that we know has lone pairs based on just its elemental Lewis dot structure, and that is oxygen. Let's talk about oxygen just again for a second. Oxygen, if we draw out its valence electrons just by itself, here's oxygen. It has 1, 2, 3, 4, 5, 6 valence electrons. 2 of them are unpaired, so it likes to make 2 bonds. And if we look at our structure, that oxygen is making 2 bonds, so it is happy. However, it has 2 sets of lone pairs. So in this case, when asked to draw the full Lewis structure, we should include the lone pairs as well. So I'm going to add those lone pairs in to the oxygen and make sure they are shown. Okay, so that was it for our example on expanding a bond line formula. We're going to go in reverse here. So here I have given you the fully expanded formula, and I want to draw it in its condensed form with just the lines. So first of all, I'm going to count how many carbons I have because those are each going to be a point. So I have 1 here, 2, 3, 4, 5. Now, I think the simplest way is to just draw the longest line you can, which is from here to here to here. And each of those is a point. Now, usually the way to do this that makes it easy is you start with your point and you go up or down, your decision on the first, and then you're going to alternate between going up and down. So here's 1, 2, 3, 4. That's the longest line I have. And we don't want to forget about this guy down here. He is connected, if you see, onto the second one. So here's 1, 2, 3, 4. You're just going to draw a line and connect him there. It doesn't matter what direction he's facing. Notice that it's facing a different direction from our original one. This corresponds to the exact same thing. And in fact, if you look at the shape in our original, there's this kind of Y shape, right? And then we have a line here and a line here between 2 and 3 and 3 and 4. So this is the exact same thing. Okay, so now I'm going to add in any other double bonds, other lines that you see. So let me get this out of the way so you can see a little bit better. Any other double bonds that you see. And you can see here between these 2 carbons, again, I'll write the numbers 1, 2. Between 2 and 3, we have a double bond. So this is 1, 2, 3, 4. Okay, there's that one. And we also have, on the very last carbon, a double bond to an oxygen. So I need to draw that double bond oxygen. And I'm not drawing any hydrogens. Remember, no hydrogens should be drawn. So to draw this just a little cleaner, because I don't want to add my big bulbous points for carbons, we'll just draw them as lines. Should look like this. Now I know it looks a little bit naked here on the end because there are no hydrogens, but that is the correct way to draw that without hydrogens. Hydrogens, remember, are always assumed. It looks a little bit odd, but that is the correct way. So this is your final condensed formula there, bond line formula.